Hello and good day, Algebra. We are kicking off Unit 9 with some radical expressions. Radical in the sense that they're square roots, and radical in the sense they are truly quite radical. And really, what's going to determine your success in this objective is kind of revisiting, understanding how we've worked with roots before. Now, we didn't actually have pre-algebra CO12 together because I didn't teach you a pre-algebra, but no doubt you understand perfect squares, right? We use them with parabolas. We know kind of what roots tell us to do. The root of 36 is 6. The root of 121 is 11. It's what number times itself equals the given root. Okay. We did, however, way back in CO2, we estimated radicals by just kind of taking a broad guess at what the decimal value of the radical is going to be. It's impossible to write the decimal value of a radical completely accurately because any non-perfect square is an irrational number. It goes on forever. So by estimating, we said round to the nearest tenth. Root 19, who's got a good estimate of what that would be? Brent? 4.4, 4.3, somewhere in that range. Root of 200, what would you estimate that to be? Root 200. Brent again. 14.6. I would argue against what? 0.2. Okay. And how are you coming up with these?
Trusty calculator.
Yeah. So putting them into a calculator definitely gives you the answer. But how do we talk about doing it in CO2? Because remember, you probably don't, but on this test you could not use a calculator, so you had to be able to do it mentally. Josh. Right. We care about those perfect squares, which in this case is 196, and the next largest perfect square is 225. Because root 196 is 14 and root 225 is 15, we know that root 200 is somewhere between 14 and 15, and then we look at how close it is to the 196, and that's how we get the 14.2 instead of like 14.7 or something like that. Okay. Root 44, estimate for that, someone who didn't use a calculator because you really want to impress us all. Sure, 6.7, 6.6, somewhere around there. But again, to accurately do this, you need to know those perfect squares that surround 44. And your success in PO61 is really going to come down to your understanding of factors and perfect squares. Okay? Because the disadvantage to estimating is that our value, it really isn't accurate. Like we said, these decimals go on forever. 4.4 is just an estimate. We lose accuracy whenever we round something. So next year, those of you going into geometry or algebra 2 or more algebra or whatever your path may take you, you're going to be asked to simplify these square roots. Okay, which means we're keeping the value intact. And so for a number like the root of 45, what we're looking for here is we're looking for factors of 45 with one of them being a perfect square. So if I just ask you for factors of 45, you might write root 3 times root 15, or you might write root 9 times root 5. I don't know why I put that multiplication symbol on front there. Right? Both of those pairs are factors of 15. And mathematically, it's legal to break this 45 into its factors as long as we keep them under the roots. Okay? Just like 3 times 15 is 45, root 3 times root 15 equals root 45. But I want the factor pair that has a perfect square. So which one am I using? Brent? Root 9 times root 5. And the reason why I want that perfect square factor is I really can't do anything more with the 3 and the 15. They're both non-perfect squares. I suppose I could write root 15 as root 3 times root 5, but I really can't go any further. But with that perfect square 9, I know the value of root 9 is 3. Right? The square root of 9 equals 3. And then the root 5, I can't do anything with, but that's okay. My simplified answer is 3 times root 5. Now, if you're saying, well, that doesn't look a whole lot simpler than root 45, what was the point of this? Again, like we've seen in other units, this is kind of the grunt work. This is the opening practice, the skills that will allow us to do more stuff later on. Okay? Any questions on that? Like I said, if you know your factors and you know your perfect squares, it's really just running through them until you find the right combo. The root of 20. What's a factor pair of 20 that contains a perfect square? Lucas? Root 4 times root 5. We don't want to use 2 and 10 because 2 is not a perfect square and neither is 10. But root 4 times root 5, we've got that perfect square with the root 4. The root of 4 equals 2. The root 5 we can't do anything with. We don't care. It just tags along. And we've got 2 root 5 as our simplified answer. Root 700. What's a factor pair of 700 that contains a perfect square? Quinn? 100 and what? It wouldn't be 70, it'd be 7. Yeah, 107. Okay, root 100 times root 7. Root 100 being that perfect square. That's 10. And then we've got root 7 tagging along. No, I mean, no, it's not coming off of the quadratic formula. This probably seems, a little bit easier, just a lot less steps. But again, if you know your factors and you know your perfect squares, that's the prerequisite skills needed here. Yeah.
So on the test, are we allowed to use a calculator?
You will be allowed to use your calculator on the test. So, I mean, if you want to check and see if you're correct, put root 700 into your calculator, whatever nasty decimal that ends up being.
Yeah.
Take 10 times root 7, and whatever answer you get should just match it.
Okay.
Yeah. Root 72. What is a factor pair of 72 containing a perfect square? Julia. Root 9 times root 8. Is there another? You knew one like this had to be coming along, right? Yeah. Is there another? Swicky?
Root 36 times root 2.
Root 36 times root 2. Is there another? Lucas?
Root 4 times root 18.
Root 4 times root 18. Uh-oh.
Okay, maybe it matters what one you do.
Unfortunately, I shouldn't say unfortunately, but yes, it does matter which one you use. Those of you that, we've talked about this a little bit in geometry thus far, which one of those three, because they all do fit the factor pairs, one being per square, which one of those three should we use to simplify this? Why 36 and 2? Because it's the largest perfect square. Okay, it's the largest perfect square. If we use 36 and root 2, the root of 36 equals 6, and then our root 2 comes along. That's our final answer. If we use 9 and root 8, and we simplify the root 9 to give us 3, this is simplified, but it's not in simplest form. Because you look at that root 8, what are the factors of 8? 2 and 4. What's 4? A perfect square, right? So if you don't use the largest perfect square, you'll find that you can simplify your root again. And so if we do that, if we take our coefficient 3 and then break root 8 apart to be root 4 times root 2, okay? All I did here was I started with root 9 times root 8. I made root 9 to 3, brought down my root 8, Then I looked at root 8 and I saw, uh-oh, there's a perfect square factor of 8. So I kept my 3 and then just separated root 8 to be root 4 times root 2. What's the root of 4? 2. What's 3 times 2? 6 root 2. Okay. The same thing would happen with that root 4 times root 18 if we worked it all out. It's kind of like if I gave you the fraction 10/20ths and I said, simplify that, or what's that in the simplest form? And you wrote 5/10. Did you simplify it? Yeah. Is it in simplest form? No, because you didn't divide by the greatest common factor. You divided by 2 and divided by 2, but that's not the greatest common factor. You would divide by 10 and by 10 to get it down to simplest form. That's the same idea here. You want to find that largest perfect square to use. If you don't find the largest perfect square, you can still get to the answer, but it's going to take a couple more steps. Okay? Root 27. Factors of 27, 1 being a perfect square. Gabby. 9 and 3. So we have root 9 times root 3. What does that simplify down to be? Some of you haven't heard from me yet today, perhaps. I feel like we've heard from you every day.
No.
Just, okay. Josh, finish it out. 3 root 3 is right. Okay. Question so far? But then you look further down the page, and then we have fractions. Well, math is always fun until you throw a fraction into it, right? Oh, don't look at the next page, though. Let's not scare you too. Let's just stick with, we'll pretend it doesn't exist, okay? No, next page. Okay, so the cool thing about the root of fractions is that we are able to kind of split this up into the root of the numerator over the root of the denominator and treat them separately. So taking the root of the entire thing is the same as taking the root of the numerator over the root of the denominator and treating them separately. Do you have a question?
One of the questions, if you have two perfect roots or whatever they're called, do you just leave them as is?
Yeah, good question. I'll come to that after we do them here. So we can rewrite this to be the root of 27 over the root of 16. And we're going to deal with each of those separately. What do you notice about the denominator? And then you look at the other fractions and you realize, oh, whew, Evan, it's a perfect square. So the denominator is pretty easy, right? You can take the root of 16 to be 4. And maybe this is where Bridget's question was. If you try and break down root of 16 and you write the root of 4 times the root of 4, and you're noticing that, is this where it came from? Yeah. Mic off. If you break it down and you notice that both of your factors are perfect squares, it means that you had a perfect square to start with, right? So root 4 times root 4, since they're both perfect squares, it means that the number you started with, root 16, is also a perfect square, which it is. We can make that directly 4. Okay. If you did do it this way, well, the root of 4 is 2, and the root of the other 4 is also 2. What's 2 times 2? 4, right? So you can still do it. It's just a little bit more work than is necessary. And then we actually just simplified the root of 27 in our last one. That ends up being root 9 times root 3, or 3 root 3 over 4, and that would be our final answer. Okay. Let's do root 80 over 25 as the last one that we'll do together. Being the root of a fraction, we can break this up and write it as the root of the numerator over the root of the denominator, which again, look at that denominator, and I like what I see. What's the root of 25? 5. That's done. And then as far as 80 is concerned, factors of 80, one of them being a perfect square. 8 and 10, it's a factor pair, but no perfect squares in that. Julia? 16 and 5, is 16 the largest perfect square? How can you tell if the perfect square that you chose is the largest perfect square? Evan?
If the second one is not a perfect square, it can't.
Right.
be simplified.
If you look at the second one and say there's no way to simplify that, then you know that you picked the largest perfect square. The other option for 80 would be root 4 times root 20, but you look at that 20 and you think, oh, 4 times 5. So I can simplify that further. That means that 4 is not the largest perfect square. So 16 and 5 is the option that we want to use here. So root 16 times root 5. Root 16 is the one that we wanted. That's our perfect square. That gives us 4. Root 5 over 5. Can we cancel out the root 5 and 5? I mean, they're both 5s, right? One's the root of 5. So they're not the same value, right? The root of 5 is not the same as 5. So we could not cancel them out, and that is going to be our answer. Okay. Your homework for tomorrow is just going to be this first page of PO61. We will tackle the variables tomorrow. Literally tackle the variables tomorrow. Final questions on this, Soybe?
Can we turn the page now?
You do not need to turn the page. There's nothing for tomorrow that is on the second page for you.
Still look at the
The only thing on the second page is anticipation for what comes next. Okay. All right, that is How You Math.